Hi, and welcome to 6.2 Universal Gravitation Ratios. In this lesson, students will be able to calculate the gravitational force of attraction between two objects in their heads. Yeah, you remember that formula? Fg equals, look at this thing. And there's like all these different numbers these could all be. You're going to do this whole thing in your head. Yeah, and this is 6.67 times 10 to the negative 11. You're going to be doing this stuff in your head. Well, kind of. So there's 6 cases of universal gravitation that we use to introduce this concept of being able to look at these ratios in your head. It's the relationship between mass and the force due to gravity, and the distance between the two masses and the force due to gravity. So what is the ratios? What is the relationship there? So we're just setting it up. Case number 1 is the base case. It's just the original quantities here. We got uh, two masses separated by a distance r, and that gives you a weight of Fg. So in these next 5 cases, we're going to change some of these variables and say, oh, what happens to the weight? So that's how we're like kind of doing it in our head. We're going to calculate what happens to the weight here. All right. So case number 2. Now we're going to double both masses. If you double both masses, what happens to the weight? All right, and here's the setup that I like to use. So instead of writing all the variables really close to each other, I like to leave myself some space. So I recommend writing it down like that. We can change the variables. We could change one or both of the masses. We could change the distance between the two. And I'm going to change the weight, therefore, right? So if we double both masses, we have double M1 and double M2. Well, now this is an unbalanced equation, right? We can't just say, oh, it's definitely equal to Fg still. All right. We change something on one side of the equation. So whatever you do to one side, you have to do to the other. So let's look at what we did. We put a 2 times, it's being multiplied by this mass, times another 2. So we put a 2 times 2 in the numerator on this side of the equation. We need to put a 2 times 2 in the numerator on that side of the equation, all right? Or what's 2 times 2? 2 times 2 is 4. So Fg becomes 4 times as big. In the base case, if we knew that Fg was 100 newtons, how big is the force due to gravity now if you double both masses? Well, it's 4 times as big. So this is 4Fg. 4 times 100 newtons is 400 newtons. So if you double both masses, you can see what happens. Now I just made this number up, right? So I'm just saying that's how it's useful though, is because you know the factor by which it's being changed. So if they actually told you what the weight was originally in the problem, then you could just use that simple factor instead of multiplying everything out using the equation. All right, let's look at case number 3. So now we're going to have both masses. See if you could pause the video here. For all of these, pause the video and then see what you can do. So it's having both masses. First of all, is the weight, do we feel in our gut, is the force due to gravity going to increase or decrease? If there's less mass, do we think the force due to gravity is going to increase or decrease? If there's less mass, then we would expect this to decrease, because it's a direct relationship. So whatever one does, the other does. If this increases, this increases. If this decreases, this decreases, right? Well, like the multiplication total. Anyway, so having both masses, you have a what's 1/2 times 1/2? Do you remember how to multiply fractions? This is like a little fraction review. All right, so when you're multiplying fractions, you do the numerator, 1 times 1 is 1, and then the denominator, 2 times 2 is 4, and that's left with 1/4. So we have 1/4 in the numerator, and nothing changed down here yet. We're not changing the radius yet, so it's just 1/4 as big. That's what's happening to the weight. And like we predicted, all right, the weight decreased. It's 1/4 as large now. What happens if you keep the mass the same? So we're not changing the mass anymore, but we're doubling the radius. As you can see, it's much further away. So the radius, you could see, is getting larger. The radius is being twice as big. Well, would you expect to happen to the force due to gravity? If these things are so far away now, are they going to like have as big of an impact on each other? Are they going to have the same, like more or less force due to gravity? What's going to happen to Fg? Well, if it's further away, we would expect Fg to decrease. And if we put a 2 in the denominator over here, that means it's like 1/2 as big. So the way I wrote this, some people are going to be like, why don't you just put it like that, make your fraction like that? We're kind of like filling in the blanks though, so I'm going to write like this. It's 1/2 as big. There's a 2 in the denominator over here. All right, sorry if that's confusing. You could also take Fg and just go, okay, Fg, there's a 2 in the denominator. I'm dividing it by 2. All those different ways of writing that are fine. It's just decreasing by a factor of 2. So it's 1/2 as big. Oh, man. I just made a mistake. I can't believe this. What should I do? Should I pause the video and restart it? Nah, I don't know. I'm going to keep going here. All right. This is a very long-winded, even though it's pretty short. What was the mistake? Can you see? Learn from my mistakes here. I'm rushing through this thing. This is a classic physics blunder we got going over here. Mr. Nangle, what the physics? This radius is being squared. So I don't just have a 2 in the denominator. I have a 2 that's being squared. R times R. 2R times 2R. 2R times 2R. That's 2R squared is equal to what? 4R squared. I have a 4, a magnitude of 4 in the denominator here. So this is 1/4 as big. I almost made that huge mistake. Did you learn from my mistake? I hope you did. I'll say that I did that on purpose. Even though I'm not ashamed. That was a little physics blunder. I made that mistake, you know? I'm doing multiple things at a time here. But don't you make that mistake now, okay? The radius is being squared. That is the universal gravitation uh, formula. R is being squared. It decreases by a factor of R squared as you go out. So you have to make sure you take that into account and square whatever number is down here when we're doing this exercise. Okay? That's a little tricky. We'll see what happens in the next one. Oh my gosh, now we're halving the radius. Halving the radius. Now, don't fall into the trap that if it was Mr. Nangle from a couple minutes ago, I would have went 1 over 1/2. Oh, that's great. Oh, no, 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 no. First of all, we have to square this 1/2 because it's being squared. All right. And then I already went over how to multiply fractions. 1/2 times 1/2 is, okay, multiply the numerator. There's a 1 times 1 is 1. 2 times 2 in the denominator is 4. So really it's changing by 1/4. Okay, I got that, Mr. Nangle. I understand. All right, but do you understand this? That 1/4 is in the denominator. So it's an improper fraction. 1 over 1/4. And that just looks crazy to me. So how do you deal with improper fractions? Do you remember? Some people learn it like this. What they do is they do a little keep, change, flip. Did you understand? You remember that? Keep, change, flip. This is just like a little fraction review. So how would you do that? You keep the number on top. So we keep in the number 1. We're changing the division. We're changing to multiplication. And then you flip. 1/4 becomes 4/1. So what's 1 times 4? 4. Okay, so that means this improper fraction becomes it's 4 times as big now. Would we expect that? I thought this decreased. Now you're saying it's much bigger? Take a look at the diagram. Look how close those masses are. Okay? It's not even, I should have wrote this in 1/2. This is 1/2 over here. 1/2 R. So they're really close to each other, which means the force due to gravity is going to be larger. they're going to impact each other more. So the closer you are, the more weight you have, the more force due to gravity. So, and it's a squared relationship. So it's 1/2 the radius, but it's 4 times as big as we described below. Man, that's some tricky stuff. But you want to know what is really tricky? Case number 6 is known as the trick. I want you to double both masses and double the radius. I know you haven't been pausing the video. Pause the video now and figure it out. And if you have been pausing the video, good job. Thank you for listening to what I said before. So if you double both masses, did you pause it? Now this is the answer now, okay? Let's put the 2's where the masses are. So double this mass, double that mass, okay? And I'm doubling the radius. I should have put a 2 over here. I'm doubling the radius, okay? It's far away, but the masses are larger. Well, what do I have in the numerator? I have a 2 times 2 in the numerator, so I have a 4. And what do I have in the denominator? I have a 2 that's being squared. Don't forget that it's being squared like I did before. All right, so 2 squared is 4. And what is 4 divided by 4? 4 divided by 4 is 1. This is the trick because it actually doesn't change the weight. If you double the masses, that's going to cause Fg to go up. But if you increase the distance between them, if you double the radius, that's going to cause Fg to go down. So the two kind of cancel each other out, and you're left with the same weight. Oh man, that's really tricky. But do you know what's really even trickier than that? Case 7, the secret anti-trick. So you thought there was only 6 cases, but there's this 7th one. I want you to double both masses and halve the radius. Pause the video and see. Okay, so hopefully pause the video. And we are going to double both masses. So, okay, all right, okay. And having the radius, oh my gosh, I hate these fractions. Oh my gosh. Let's just write it out, you know, and then we're going to have to deal with an improper fraction. So 2 times 2 is 4. 4 is in the numerator. I wrote a 1 over 4 here. I'm messing up all over the place, but that's okay. All right, it's halve the radius. I'm getting ahead of myself. Sorry if that was confusing, okay? Having the radius, I'm getting ahead of myself because what's 1/2 squared? We did it before. What's 1/2 squared? 1/4. Okay? Look at this improper fraction. What a mess. So what we're going to do is keep the first 4. Change the division to multiplication, keep change, and then flip over here. All right? So this becomes 4 over 1. What's 4 times 4? 16. So what happens is you're 16 times as big because this is really what the diagram looks like. You're 16 times as big because not only are the masses super large, but the radius is super small. And those things cause the force to increase to such it's 16 times as big as the original base case. Pretty crazy stuff. Isn't this fun? This is fun doing this in your head, right? Yeah, hopefully that mistake, but that everybody makes mistakes and you just learn from your mistake. Now, I happen to already know that this is being squared and I just forgot. So also don't be forgetful, but learn from your mistakes too. And don't be ashamed of your mistakes because some people might learn from them. Like hopefully you learn from my mistake. All right, I did want to talk about, so, it's nice to do the math in your head, blah, 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 but what are the relationships in terms of a graph? So pause the video here and try to predict what you think these 3 graphs will look like. Graph number blue. If you increase the mass, what happens to the weight? The mass and the weight have a direct relationship because they're both in the numerator. You could think of it that way. So it looks like this. Direct relationship. If I double this one doubles. All right. If this one gets smaller, this one gets smaller, 1/2. All right. So it's a direct relationship. What happens with graph number red? All right. If the radius increases, meaning the things get further apart, they're getting really far apart now. What happens to the weight FG? Is it going to increase or decrease? What does the graph look like? Looks like that. So basically, if I double the radius, that means it's 1/4 as big, 2 squared. So not only is it an inverse, inverse really kind of looks like this. An inverse square is just more pronounced. That's really exaggerated, but you're never going to have to pick out the difference between the two. Like this, to me, looks more like an inverse relationship instead of inverse square. But that is totally fine. All right, and how about this last one? Graph number purple. If I increase the distance between the masses, will that have an effect on the masses themselves? So the masses went from over here to being further apart, the radius increased. Did that affect the mass? Hopefully you're saying to yourself, no, that's a weird thing to ask, but yeah, the graph just looks like that. Yeah, the mass stays constant. Okay, so that's just some ways that they might try to trick you because they're being super mean sometimes when they're asking about these graph things. All right, one more thing I wanted to say was that it's an inverse square relationship. And it comes from the fact that the gravitational field, or any field force really, like we talked briefly about magnetism and electrostatic, how you feel like static electricity, you could feel that sometimes, or playing between magnets. Those are non-contact field forces, and they emanate in a spherical fashion. So if you take the area of a sphere, it looks like this. See this r squared? The distance has an effect on the surface area. So it's called, I think it's like Gauss stuff. And yeah, so if you think of it like gravity is a spray can, like spray paint, right? The closer the paper is, like if it's a really small diameter here, let's draw it like this. If it's a really small diameter, then this is going to be very concentrated. But as you go out, it's not as concentrated anymore. Then it's less, it's over a larger area. All right. And yeah, it's over a larger area. It's the same like amount of gravity spread over a larger area, if it helps to think of it like that. I'm just trying to show that it's like an inverse square relationship without getting too much into the math of it, right? But the closer it is, the more it is, the further apart, the less. It has to do with r squared. Can you tell I'm making this video at the end of the day and I'm really tired? That's about it. Thanks for watching and have a great day.